Alrighty, so welcome back. Today is going to be a quite fun day. You're going to enjoy variation of parameters. It's going to look like magic at the end. But before we get to that, which I cannot wait to show you, let's knock out the homework from the last one. That was the method of undetermined coefficients, where you had a non-homogeneous equation with constant coefficients. So I think I had 3, 19, and 29. So let's knock out number 3 to start. All right, so for 3 we had y double prime minus 10y prime plus 25y, and that equals 30x plus 3. A nice simple one to kind of get started on. So first thing we do is we solve the auxiliary so we can get the complementary solution. So m squared minus 10m plus 25 equals 0. Well, that's going to be m minus 5 quantity squared equals 0. So m equals 5. So that means that the complementary solution is going to be y sub c is equal to c1 e to the 5x plus c2 x e to the 5x, since we had repeated solutions. So there you have, that's our y sub c. And now we need to worry about the y sub p. And how do we do that? Well, we make a guess. I can come over here and say, I think my y sub p is of the form, based on the non-homogeneous part, ax plus b. That would mean y sub p prime is a, and then y sub p double prime, which is 0. Okay? So now I can plug that in to this differential equation up here and have y double prime 0 minus 10 times my y prime, which is a, plus 25 times y, which my y is ax plus b, and that equals 30x plus 3. Now I can group terms, and if I do that, I can go with, let's see, that's going to be negative 10 equals, oh wait, let me distribute first. I'm going to get in trouble if I do that. I'm going to miss terms. So negative 10a plus 25ax plus 25b equals 30x plus 3. Alrighty, so let's do the x terms first. So 25a equals 30. Those are the x terms. And now for the terms that don't have a variable, we've got negative 10a plus 25b equals 3. All right, we can solve that. That means a is equal to 6/5, and then I plug that in here. I'm going to get negative 12 plus 25b equals 3. Swing that over. I'm going to have 25b equals 15, which means that b is, what is that, 3/5, something like that. Alrighty, so now I can write my final solution. Let me do y sub p up here. Y sub p then is equal to, well, I've got my b and my a that I need to fill that out with. So y sub p is going to be 6/5 x, and then plus b, which is 3/5. So 3/5, just like that. So now my complete solution, if you will, the one that has the complementary and the particular all put together, is going to be c1 e to the 5x plus c2 x e to the 5x plus 6/5 x plus 3/5. And there you have it. That is our solution to this non-homogeneous DE with constant coefficients. Not too bad, not too bad. Alrighty. I say that, and then there's 19. Woo! Let me clear this and let's tackle it. Alright. Okay, so 19 is, it's going to be a little bit of work. So it's not hard, it's just a lot of work. So we have y double prime plus 2y prime plus y equals sine of x plus 3 cosine 2x. And this is where you're like, ugh. So I can already see my guesses are going to be many. Here we go. Let's go ahead and solve the auxiliary. So m squared plus 2m plus 1 equals 0. That's going to be m plus 1 equals 0. And that means we have m equals -1, but it's repeated. So y sub c is going to be just like we had before, c1 e to the negative x plus c2 x e to the negative x, like that. Okay, so we've got our complementary solution ready to go. Now let's work on our particular solution. So here's the problem. And it's not a problem, it's just a lot more work. I have sine of x, and then I've got cosine of 2x. They're not the same, so I'm going to have to build my guess with sine x's and cosine 2x's. So here we go. My guess is going to be, and I hope I can put all this on the screen, y sub p is going to equal, well, a sine x plus b cosine x. That takes care of this term. Now we go plus c sine 2x plus d cosine 2x. That takes care of this term. So now we take the derivative. Y sub p prime is equal to, well, we're going to get a cosine x minus b sine x plus 2c cosine 2x minus 2d sine 2x. Okay? Then y sub p double prime. Well, we're going to get negative a sine x minus b cosine x minus 4c sine 2x, and then minus 4d cosine 2x. Whew. Now for the fun part, because we have to build this dE using these. Here we go. Y double prime. And this is going to be over 3 lines, so it's just going to have to be that way. You know what? I'm going to clear or just array. Gosh, it's so much work. I'm going to write it down here and then I'll erase up so I don't have to write it twice. So here we go. Y sub p double prime minus a sine x minus b cosine x minus 4c sine 2x minus 4d cosine 2x. It's the first one. Then plus 2 times y prime, so times this, so it's going to be a cosine x minus b sine x plus 2c cosine 2x minus 2d sine 2x. But wait, there's more. Now we need the y term. So plus the y term. A sine x plus b cosine x plus c sine 2x plus d cosine 2x. And all that is equal to sine x plus 3 cosine 2x. Alrighty. So what I'm going to do is erase, oh gosh, what do I want to erase? I'm going to erase all of this and leave this down here and this up top so I don't have to rewrite it. So let me see if I can get away with that. Erase all this. My cats are zooming behind me, so if you hear galloping, that's a cat. At least they waited until I woke up to start zooming. That is very nice of them. So, alrighty. Here we go. So, now I need to gather my like terms. Let's start with the sine x's. So, if I start with the sine x's, I want to turn my page so I can actually follow along so I don't make any mistakes. But then again, I never make mistakes, so it's all good. Here we go. All the sine x terms. Well, I've got negative a, gone. Let's see, minus 2b, gone. And then plus a. And this is sine x, so it equals the coefficient right here, 1. Alrighty? That's not too bad. Now, let's worry with the cosine x terms. Oh wait, I forgot to cross out my sine x, didn't I? So that one's gone, and that one's gone. We've taken care of it. So now cosine x. So I've got negative b, gone, plus 2a, gone, and then plus b equals 0. Okay? Then I'm going to do the sine of 2x. So the sine of 2x is going to be negative 4c, gone, minus 4d, and my dog started barking, awesome. Okay, I just closed the window so maybe the noise is a little bit less. So we had negative 4c, and then we're gathering the sine 2x's, so minus 4d, cancel that one, plus c, and that equals 0. Get rid of that one. And finally, we're going to have negative 4d, gone, plus 4c, gone, plus d, gone, and that equals 3. Alright, so negative a, positive a cancel. I'm left with negative 2b equals 1. Negative b, positive b cancel. 2a equals 0. And then this is going to give me negative 3c minus 4d equals 0. And negative 4, oh, sorry, that's going to be negative 3d. Negative 3d plus 4c equals 3. All right, well, I can solve these. B is going to equal negative 1/2. And then A is going to equal 0. That's not too bad. And this is just a system of equations. I'm going to rewrite this one under this one. So 4c minus 3d equals 3. I'm just going to use elimination. Multiply this one by 4 and this one by 3. So when I do that, I'm going to wind up with, let's see, what is that? Negative 12c minus 16d equals 0. And then positive 12c minus 9d equals 9. So when I add them together, the c's are going to cancel. I'm going to be left with negative 25d equals 9. D equals negative 9/25. Okay, so now I can assemble what my y sub p actually is. My particular solution is, let's say I had a times sine x, so a is 0, so the sine x term is going to be gone. It's going to be a 0 for that one. And then plus b, so minus 1/2 cosine x. And then I've got c. Where's my c? Oh, I haven't solved for c. Hold on, I got to solve for c. I've got my d, I didn't solve for c. Let's use this one, the 0 one, that'll be easier. Negative 3c minus 4 times negative 9/25 equals 0. Alrighty, let's see. For that one then, I'm going to wind up with negative 3c is equal to, it's just 36 over 25. So equals negative 36 over 25. Divide by 3, negative 3, I get c is equal to positive. It's going to be what, 12 over 25? Think so? Alrighty, so plus 12 over 25 sine 2x. And then the last one is my d, so minus 9 over 25 cosine 2x. Alright, so now let's put it all together. Y equals c1 e to the negative x plus c2 x e to the negative x minus 1/2 cosine x plus 12/25 sine 2x minus 9/25 cosine 2x. And there you have it, right there. That's our solution. And it looks like a lot, because it was a lot. Those sines and cosines were driving me crazy. So hopefully that one, not too bad. We can now drop back into a much simpler example for the last one. So, yay! Let me clear all this and let's tackle that. Clear that. So for 29, we had, let's see, what it was, 5y double prime plus y prime equals negative 6x. Alrighty. Oh, and this is solving for initial conditions. That's cool. So y at 0 is 0, and y prime at 0 is negative 10. Okay. So first let's solve the auxiliary. So 5, if I don't mess up, 5 m squared plus m equals 0. I'll factor out an m. We'll have 5m plus 1 equals 0. So m is going to equal 0, and m is going to be negative 1/5. So y sub c is going to look like, it's going to be c1 e to the 0x plus c2 e to the negative x over 5. But e to the 0 is just a 1. So it's just c1 plus c2 e to the negative x over 5. That's our y sub c. Now let's worry with our, and you know what, let me write that out because there's a reason. c1 plus c2 e to the negative x over 5. Okay. Now, y sub p, what is my guess? Well, there's just an x term over here, so my guess would have been ax plus b. But it's not ax plus b because I already have a constant in my y sub c. So that b won't work. So I need to bump it up one level and make my guess ax squared plus bx. Now, just to recap, why didn't I do y sub p is equal to ax plus b? That b is a constant. That c1 is a constant. Therefore, I can't have my guess containing part of my y sub c. So that's why I have to bump it up a level right here. Alrighty? So y sub p prime is going to be 2ax plus b, and then y sub p double prime is just going to be 2a. That's not bad. Okay, so now I can build my dE. So this is going to be 5 times 2a plus y prime, which is 2ax plus b, and then that is going to equal negative 6x. Okay, so now I can gather my terms. I'm going to get 2a equals negative 6, and let's see, 10a plus b equals 0. Okay, so a, if I solve out, is equal to negative 3. Plug a negative 3 here, I get negative 30. Swing it over. B is equal to positive 30. Okay, so that means my y sub p is equal to, I've got a x squared, so negative 3x squared plus 30x. Okay, now that means my full solution is going to be, oh, can I fit it in? I think I can fit it in. Y equals c1 plus c2 e to the negative x over 5 minus 3x squared plus 30x. Okay, but I have these initial conditions up here, so I can plug them in to find what my c1 and c2 are equal to. So let's start with the first one. So I'm going to have 0 is equal to c1 plus, plug a 0 for the x here, this whole term becomes a 1, so c2 minus, this is going to be a 0, this is going to be a 0. So what do I wind up with? I wind up with c1 is equal to negative c2. Okay? Now I go for the second one, but to go for the second initial condition, I need to take the derivative of y. So y prime is going to equal, c1 is going to drop because it's a constant. This becomes negative 1/5 c2 e to the negative x over 5, and then minus 6x plus 30. Okay, so now when I plug in my initial condition, oh, I'm going to run out of room, I think. I'm going to try to fit it in right here. Sorry for the crowding, but I really don't want to clear this and start again. So if I plug in this initial condition, I'm going to get negative 10 equals negative 1/5 c2. Again, this term goes to 1. This is a 0, and then I'm left with plus 30. Swing it over. Negative 40 equals negative 1/5 c2. That means that c2 equals 200. And that also means that c1, no, I do not have enough room for this. c1 is negative 200. Alrighty, so now I have my c1 and c2 values, so I can plug them in right here, and I'm going to get, see if I can do this. Y equals c1, negative 200, plus 200 e to the negative x, I swear that's an x, e to the negative x over 5 minus 3x squared plus 30x. Hey, what do you know? We fit it all together. That's my solution right there, my final one. Alrighty. Hope you enjoyed that one. That was fun. I always enjoy dealing with initial conditions so you get the actual solution. Alrighty. So now that's all the homework. We can dive into the next thing. Ooh, we're going to have fun. Here we go. Clear this. So let's see. This is 4.6 or 0.6. And it is variation of parameters. Did I do the right title for the initial thing? Hold on, let me look. Okay, good. I did write that. I was like, did I do the right one? I'm not sure. So variation of parameters. So this is actually an extremely elegant way to find your solution. It is, it takes some doing to get to the derivation, get through it. But when you're done, it's extremely satisfying and super quick. And so it all starts with the kind of the assumption that maybe we can replace our C1 and C2 with some variable parameter, variation of parameters. So that's how the whole guess is. The whole thing for this one is, can we use functions that can vary to represent our C1s and C2s? So let's get to it. Buckle up. This is going to be a crazy ride. Let's start off with a very simple expression. We're going to do dy over dx plus 2y equals 0. Okay? Well, if I look at the auxiliary of that, I could solve it that way pretty quickly, right? So if I've got that, I'm going to say y prime plus 2y equals 0, m plus 2 equals 0, m equals negative 2, right? So y is equal, that's not an equal sign, that's an e. Y equals e to the negative 2x, like that. Okay? Now, let's say that I didn't know this method, that I had forgotten, and I had my dy dx plus 2y equals 0. Do y'all remember the fastest method that we used to solve if we didn't know this auxiliary method where we have constant coefficients? Right. So what's the word? Well, two words. Integrating factor. Yes, absolutely. So if we did it that way, we're going to wind up with our y equals c1 of e to the negative integral p of x dx, because the f of x is 0 over here, so it's just going to be a constant. So that's what we would get if we use the integrating factor. All right. So now let's do what would happen if we didn't have it equal to 0. Okay. So now if it doesn't equal to 0, we've got dy dx is equal to 2, when I say equal, my dog's barking is driving me insane right now. So plus 2y equals something that is not 0. Well, then we have to do the whole thing where y equals, we're going to wind up with e to the negative p of x dx. This is just 1 over mu times the integral of mu e to the integral of p of x dx times f of x dx, right? I guess I should fill that in with an f of x since it's just calling it a box. So we would get this thing right here. That's how we would solve out, right? Okay. So first thing I want to do is say, if I'm looking at the homogeneous first order equation, it looks like this. dy dx plus p of x y equals 0, right? Okay. I want to box that in, and I'm going to call that star 1. Okay, so everything up to now has just been a little meandering. It all comes into play in just a second, I promise. So let's say that I have this right here. That is a first order homogeneous DE. Okay? Now, here we go. I'm going to do some crazy math. You ready? Non-homogeneous. dy dx plus p of xy equals f of x. Okay? So I can now do my, I can kind of go through a long process, but I'm going to say that my y sub p is going to equal u1 of x times y1 of x. Okay? I'm no longer putting a c in front. I'm calling it u1. It is a variable parameter solution here. So u1 of x. Okay? Now, remember this is star 1, and we're going to start with this when I clear the space. So clear this. So we're going to have, let me write that again. We're going to have y sub p is equal u of x times y1 of x. Okay. Now, where's my one? I said u, did I say u of x? I meant u1 of x. Alrighty. So y sub p is equal to u1 y1. Okay. So you mind if I get rid of this p? It's going to make dealing with the math a lot faster. So y is equal to u1 y1. Okay. Now, if I take this is my y, and my function was dy dx plus p of x y equals f of x, well then I can plug in. I have the derivative of u1 y1 with respect to x plus p of x times this y, which is u1 y1 equals f of x. Okay? So I'm now going to factor out the u1s. Well, first, let me finish doing this first. All right, so this is the derivative of two functions, right? Right here. So if you'll allow it, I'm going to have first times derivative of the second. So u1 times the derivative like that, plus the second, y1, times the derivative of the first. Oh boy. u1 over dx, like that, plus p of x, u1, y1 equals f of x. Okay? Now I'm going to factor up my u1 terms. Okay? It's kind of strange, but alrighty. So if I do that, I get u1 times dy1 dx plus p of x. Because it was just this term and this term that had a u1 that I could break out, plus y1 times du1 dx equals f of x. Alrighty? Now, this is dy dx plus p of x. I am now going to invoke star 1 and call this 0. Okay? If I do that, then this whole term drops, and I'm left with this right here. So I'm left with y1 times du1 dx equals f of x. Okay? So now that I've got it into this form, I'm going to do some rearranging. I'm going to take this y1 and divide both sides by it. So if I do that, I get du1 dx is equal to f of x, f of x divided by y1. Okay? I'm also going to shift this dx over. So I'm going to have du1 is equal to f of x over y1 dx. Now I'm going to take the integral of both sides. Integral, integral. When I do that, I'm going to get u1 is equal to, well, this integral, right? So this is the integral of f of x y1 dx. Okay? Now, this is where it gets a little bit weird. So I'm going to go back to the top and say my y sub p is u1 times x1. Okay? So let me swing up to here. And I've been swinging all over the place, but bear with me. So y sub p is equal to u1 times y1. So it's equal to this times y1, right? Because that's u1. So it is equal to y1 times the integral of, if you'll allow me, I'm going to rewrite this, 1 over y1 times f of x dx. Does this form look familiar at all? I sure hope so, because that's what we did at the very beginning. Now I can say that my y1 is equal to mu. That's what it is, which is e to the integral, oh, I'm sorry, this one's going to be to the negative integral, negative to the negative mu, because it's right here, this is the e to the negative, right? The e to the negative integral p of x dx. Okay? So what did we just do? It seems like we did a lot of work for nothing, really. What we just did is we said, can we say that I have this constant function u1 in front of my y1 instead of some constant? Why did I just say constant? I say constant twice. retry. I have this u1, which is a variable parameter, times my y1. When the dust settles and I use that method, I wind up with what my solution has to be, which is this form right here, which is kind of what we already knew. So by using this crazy technique, we're able to get something that we already knew the answer to. But this isn't actually the real math. The real kicker comes in next, because the first order is really easy. It's the second order that y'all are going to just love this. Maybe not. So I'm going to clear the board. If you want, get some caffeine, look at this, what's coming up fresh, because it is so intense. All right. And yeah, we're going to suffer through all this, and we're just going to jump to, when we actually work the problems, a solution that takes about 2 minutes to knock out a second order DE. So we have to suffer first, though. I have to show you where it comes from. So here we go. We're going to clear this and start on the rough stuff. I can actually get it to clear. So here we go. I'm going to start now with a second order DE and do some of this craziness. So a sub 2 x y double prime plus a sub 1 x y prime plus a naught of x y equals some f of x. Okay, I'm going to put it in standard form, so when I do that, I'm going to wind up with y double prime plus p of x y prime. I don't know why I did a 1 there instead of a prime. Y prime plus, we're going to call this q of x y equals some f of x. I guess I should have called that like g of x up here, because I'm dividing by a2, which makes f of x. All right, this is our standard form that we have right here, right? Okay, now, once again, I'm going to put the homogeneous part up here. Y double prime plus p, you know, I'm going to get rid of the x, so I don't have to, plus p y prime plus q y equals 0. Okay, that is the homogeneous part, and I'm going to box it and call it star 2. So I'm going to use this star 2, not 2 stars. So this is what happens when you're trying to carry too many things in your head at once. You wind up running out of space and putting down silly stuff. And the whole reason that I'm distracted is because I see what's about to take place, and I don't want to mess this up. Here we go. Let's say that I have, just keep this one in mind over here. I have y sub p equals u1 times the y1 plus u2 times y2, right? Where these are my varying parameters. So u1 and u2 are varying. So that means that y sub p prime is going to equal, we're going to have u1 y1 prime plus y1 u1 prime plus u2 y2 prime plus y2 u2 prime. Okay? And to make it easier to keep track of, I'm going to change the order to where the u always comes first in the next step. Okay? So that means y sub p double prime is going to equal u1 y1 double prime plus u1 prime y. You know what? I don't do that. I said I did, and I'm not doing it on my paper. I should have. Save me a little trouble. I'm not switching them. Really? I don't switch them ever? Wow, I don't switch them ever. That is surprising. All right. Then forget what I just said up here. Let's see. We have plus. Yeah, I know y'all are like going, quit messing up, but it's there. It's just going to happen. So I've got u1, y1 double prime plus, and then I switch. y1 prime, u1 prime, that's for this term, plus I'm going to have y1, u1 double prime plus u1 prime, y1 prime plus, that was this term, u2, y2 double prime plus y2 prime, u2 prime, that's that term, plus y2, u2 double prime plus u2 prime, y2 prime. Alrighty, and I'm going on a slant. That's okay. So here we go. Let's say that we have this homogeneous equation right up here where the f of x is equal to 0. Okay? So I'm now going to fill in these three expressions into this dE. I'm going to start with the y double prime. Okay? Here we go. u1, y1 double prime plus y1 prime, u1 prime plus y1, u1 double prime plus u1 prime, y1 prime plus u2, y2 double prime plus y2 prime, u2 prime plus y2, u2 double prime plus u2 prime, y2 prime. 1, 2, 3, 4, 5, 6, 7, 8. Yep, got all the ones I needed. That's the y double prime plus p times y prime. So p times u1, y1 prime plus y1, u1 prime plus u2, y2 prime plus y2, u2 prime. Okay? Plus q times y. So that's this piece. u1, y1 plus u2, y2 equals 0. Alrighty? Whew. Now, I'm going to do some rearranging. Here we go. You ready? First thing I'm going to do is factor out the u1s. So there's one there, and one there. Alrighty? So if I factor out the u1s, I'm going to get u1 times, I'm going to get y double prime, and then the next one is right here, plus p y prime, and then the next one's here, plus q, by the way, that was y1, don't want to forget those, that's important, q y1. Okay? Now, plus, I'm going to factor out u2, same thing. So u2 starts right here, so I'm going to get y2 double prime plus y2 p y2 prime plus q y2. Okay? Now, I'm going to arrange the remainder of the stuff in a very, very strange way. Okay? So I'm going to have plus, here we go, y1 prime, oh, sorry, not prime, just this term here, y1 u1 double prime plus u1 prime y prime. Okay, so I've got these two pieces right here, so wipe those out, plus y2 u2 double prime, oh that's a y1 in it, u2 double prime plus u2 prime y2 prime, that's these two, right? Okay, wait, did I cross out the wrong ones? Ah, I crossed out that one. I didn't mean to cross out that one. That one was, that's y1 prime u2 prime. I meant this one. This is the u2 prime y2 prime. That's that one. Alrighty. This one's still alive right here. Alrighty, so now plus, let's see, what else do I have left? Well, I've got this piece right here, p times these two, right? So plus p times y1 u1 prime plus y2 u2 prime, okay, and then plus the last two terms, this one and where's the other one? That one. So y1 prime u1 prime plus y2 prime u2 prime. Whew. All right. y2 u2. That was a 2 right here, and I'm looking at it. Okay. So now I have officially used all my terms, and I've grouped them in a very strange way. All that equals 0, right? Okay. Here's where the magic happens, as you can probably already tell. What do I have here? I've got y1 double prime plus py1 prime plus qy. That's 0. So this whole term is 0. y2 double prime plus py2 prime plus qy2. 0. Same thing. Okay? So now it's going to leave us some stuff, this stuff that's down here. Alright? So let me clear, see, do I want to clear or erase? I'm going to, I think I'm going to erase. That way I can keep this going. I'm just going to erase from here down to here. So I think it'll work better that way. Alright, we're getting there. I know I should have a larger eraser, but I'm trying to be super careful so y'all don't yell at me through the screen for, ah, you just erased half the stuff. Alrighty, we're almost there. The end is in sight. It's not too bad from here on. Alrighty, so I'm going to rewrite this now. First off, I'm going to rewrite this up top here. Okay, I'm going to say that y double prime plus p y prime plus q y is going to equal f of x. Okay, so I'm going to first off set this equal to this down here that I have remaining, and it equals f of x. So let's see what I have here. Well, I've got something, well, kind of, I can't do that yet. Can I do that yet? Can I get through? I can if I do one thing, if y'all will let me say one thing. What I have here for these two terms, first times derivative of the second plus second times derivative of the first. This term, this set of terms right here is equal to the derivative of y1 u1 prime. Okay? This set of terms here, first times derivative of the second plus second times derivative of the first, is the derivative of y2 u2 prime. Okay? And I can't do anything else with the rest of this, so here we go. So I've got y double prime plus py prime plus qy is going to equal this derivative, so d dx of y1 u1 prime plus the derivative of y2 u2 prime plus p times y1 u1 prime plus y2 u2 prime plus y1 prime u1 prime plus, I'm running out of room, y2 prime u2 prime. Alright, and that equals f of x. If you can imagine me writing it right here, it equals f of x. That's just a mess. Okay, equals f of x. Alright? Okay, I think I've got everything I need now. Y double prime plus py prime plus qy equals, well, they're both derivatives of x, right? So this is ddx of y1 u1 prime plus y2 u2 prime plus p times y1 u1 prime plus y2 u2 prime plus y1 prime u1 prime plus y2 prime u2 prime equals f of x. Okay? Now, this is the derivative of this plus p times the exact same thing. I am going to invoke star 1 now and say that this and this, the derivative of this plus p times this, is equal to 0. Okay? So d dx y1 u1 prime plus y2 u2 prime plus p times y1 u1 prime plus y2 u2 prime equals 0. Well, the only way that equals 0 is if this equals 0. y1 u1 prime plus y2 u2 prime equals 0. That has to be the case. Well, if this equals 0, this piece up here, that means this piece is equal to f of x. So y1 prime u1 prime plus y2 prime u2 prime equals f of x. Okay? Look what we have here. We have a system of equations that will allow us to solve for u1 prime and u2 prime. If I can solve that, all I have to do then is take the integral, and I've got my u1 and my u2. So, and that is the varying parameter that's in front of my solution. So that's what we want. So here we go. We're almost there. I did all that work for this little box right here, which I will now erase the screen and start fresh with that little box. So let me clear this. Okay, so let's put the little box up at the top. We have y1 u1 prime plus y2 u2 prime equals 0, and y1 prime u1 prime plus y2 prime u2 prime equals f of x. Okay? So the way that we're going to solve this little system is by using something called Cramer's rule. I don't know if y'all study that in linear algebra or not. You've probably seen it even in algebra 2, maybe, something like that. So Cramer's rule, I'm going to give you Cramer's rule, or the formula, but I think it's called the rule for some reason. So let's do an example. Let's say that I have, I'll start the example here and then move over. 4x minus 3y equals 11, and 6x plus 5y equals 7. And I don't want to do the standard substitution elimination. I'm going to use Cramer's rule. So first, we're going to form the coefficient matrix. So the coefficient matrix you know what? I just had a cool idea. I'm going to do all this over here until I can do the same thing over here, and it'll make a lot of sense. I'm going to like draw a line or something down the middle. All right. So the coefficient matrix, it's just the matrix of the coefficients right here. And we're going to call that D, and it is going to be 4, -3, 6, 5. Okay? Now, the submatrix D sub x is kind of an odd thing. What we're going to do is we're going to eliminate, basically take this column out right here and work with the remaining pieces, but we're putting the coefficients first, kind of like they're wrapping over. So this becomes 11, 7, -3, 5. Okay? And dy is going to be, if we eliminate the y's, but we don't move the coefficients in front. We leave the coefficients as is, so it's going to be 4, 6, 11, 7. Okay? So now that we have all of our pieces, all we have to do is the determinants of all these. So x is equal to the determinant of d sub x divided by the determinant of d, and y is the determinant of y divided by the determinant of d. Okay, so let's just get these values. The determinant of dx is going to be 55 minus 21. That's going to be 76. Divided by the determinant of d, 20 minus plus 18 is going to be 38. And y is going to be, determinant of y, 28 minus 66, which is negative 38, over the determinant of d, which was already 38. So x is equal to 2, y is equal to negative 1. Okay, so that's how you use Cramer's rule to solve for your variables. We're going to do the same thing over here now. We're going to say that, but we're not going to call them D matrices, we're going to call them W's. So W is going to be the coefficient matrix. So it is going to be y1, y1 prime, and then y2, y2 prime. Why do we call it W? Because that's the Wronskian. That's why. Then we're going to say W sub 1, since we're not dealing with the x's here. W sub 1 is going to be, if I take this column out and put the third column in first, I'm going to wind up with 0 f of x, and then this column y2, y2 prime. Okay, then W2 is going to be eliminating this column, so it's going to be y1, y1 prime, and then 0 f of x. Okay, so now I'm solving for u1 prime and u2 prime, right? u1 prime is going to equal to w1 determinant over w's determinant, and then u2 prime is going to equal w2's determinant over w's determinant. Okay, so what do I get with this? Well, it's going to look terrible, but it's not. u1 prime is going to equal, well, the determinant of 1 is going to be 0, and then minus y2 times f of x. So this is going to be minus y2 times f of x. Okay? And then I need to divide that by the determinant of w, which is the Wronskian, right? So I'm going to go straight and just put this as that, because that's the Wronskian. Alrighty? Now what is u2 prime equal to? u2 prime is equal to the determinant of my w2, so y1 f of x minus 0, so y1 times f of x divided by the Wronskian. Okay? Whew. Now, we are almost there. What I want to do is basically box these. We just did a lot of work to get to this right here. Okay? So this is what we're going to be using to solve DEs. So let's actually solve a DE using this. Let's do an example. Woo! Here we go. Really, every bit of the work we've been doing for the past hour is this. The whole thing is just to get this right here. We didn't need, if you got lost during the derivation, or I didn't do the best job, that's for sure, because it's so complicated. You can ignore everything that's gone before, everything that I talked about except for this right here, and you're good to go. So let's go ahead and clear the screen and knock this out. So let's see. Let me make sure I write that exactly as it is. Don't want to mess that up. I want to get my pages all messed up. So we had u1 prime was equal to, we wound up with negative y sub 2 times f of x divided by the Wronskian. And then u2 prime was equal to y1 times f of x divided by the Wronskian. All right, that's all we need. Now let's work an example. So let's say that we have y double prime minus 4y prime plus 4y equals x plus 1 quantity times e to the 2x. And you can already see now why we want this new technique compared to just guessing using the undetermined coefficients. That's because sometimes the non-homogeneous parts are not pretty, and it would be terrible to try to come up with the y sub p. So we're going to use this technique up here. First thing we have to do is we have to solve out for our auxiliary. So we're going to solve for this. We're going to have m squared minus 4m plus 4 equals 0. Well, that's just going to be m minus 2 quantity squared equals 0. So m is equal to 2, but it's repeated. So I'm going to get y1 equals e to the 2x, and y2 is going to equal x e to the 2x, right? Where normally I would do y sub c is equal to c1 times this plus c2 times this. But these are our actual solutions. Why did I do it that way? Because this and this are what we have up here. Okay? So now all I have to do is to compute the Wronskian, because I'm going to need that. So the Wronskian, which I'm going to indicate like that, well, that's going to be equal to the determinant of, well, I've got my y1 is e to the 2x, y2 is x e to the 2x, right? So now what is the derivative of e to the 2x? Well, it's just 2e to the 2x. And the derivative of x times e to the 2x, first times derivative of the second, so 2x e to the 2x plus e to the 2x, right? Alrighty, so now this determinant. When I multiply this times this, I'm going to wind up with 2x e to the 4x plus e to the 4x, okay, minus 2x e to the 4x. These two cancel, and I'm left with the Wronskian equal to e to the 4x. Okay, so that's my Wronskian. Now I can build my u1 prime and u2 primes by doing, well, u1 prime is going to equal, I've got this divided by the Wronskian. Well, what is this? Well, if you remember back when we had it's right here. I don't have to remember. It's right here. So this is my f of x, right? So I'm going to have negative y2 times my f of x. So this is going to be, let's see, that is negative y2, so negative x e to the 2x times f of x, which is this right here. So x plus 1 times e to the 2x divided by e to the 4x. Okay, so what do I have here? Well, this is just negative x. I'll have to do it in 2 lines. I don't think I can get all in one. This is just negative x e to the 4x times x plus 1 over e to the 4x. Well, the e to the 4x's are going to cancel, and I'm going to be left with u1 prime is equal to negative x squared minus x. That's my u1 prime. What's my u2 prime? Well, I have to do that right here. u2 prime is going to be y1 times f of x. So y1 is e to the 2x. So e to the 2x times, well, I've got my x plus 1 e to the 2x, and then divided by the Wronskian, which we know is e to the 4x. What does this become? Well, this becomes e to the 4x times x plus 1 divided by e to the 4x. And that means that these are going to cancel. u2 prime is equal to x plus 1. Okay, so I've got u1 prime right here, and I've got u2 prime right here. Okay, so what I need now is u1 and u2. I think I can get by with all this. Would y'all be terribly heartbroken if I erased this and rewrote some? Because I don't want to be too cramped, and I'm not going to be able to fit this in if I don't. So let me take out this calculation stuff, all of this calculation. So let me make a larger brush size too, so it doesn't take quite as long. All right, so just remember u2 prime is x plus 1, u1 prime is negative x squared minus x. So let's get rid of all this. Oops, don't want to get rid of that. Leave that alone. All right. I can now write that up here. Make sure I lower that a little bit. So I had u1 prime was equal to negative x squared minus x, and u2 prime was equal to x plus 1. Okay. Now, I need to find u1 and u2. Well, u1 prime is equal to negative x squared minus x. So if I take the integral of both sides, I'm going to wind up with u1 equal, what is the integral of negative x squared minus x? Well, that's just negative x cubed over 3 minus x squared over 2. And I don't have to put the c there because I'm just working kind of abstractly with this. So that's my u1. And u2 is going to be handled exactly the same way. So u2 is going to be the integral of x plus 1, which is just x squared over 2 plus x. Okay? Now, here we go. Way, 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 way back at the very beginning of all this derivation, we said that my y sub p was equal to u1 y1 plus u2 y2. Therefore, my y sub p is drum roll, u1, negative x cubed over 3 minus x squared over 2 times y1, e to the 2x, plus u2, x squared over 2 plus x times y2, x, e to the 2x. That is it. This is my particular solution for the non-homogeneous problem. It seems like it's a lot of work until you get to this form. We knew that this was our non-homogeneous part right here. How much fun would it have been to derive this? And the reason that we would have such high orders is because I've got my y sub c right here is already taking e to the 2x, c1, e to the 2x plus c2, x e to the 2x. So that wipes out both of these initial pieces. I would have had to go up to an x cubed and an x squared for my guess and work through all of this. But it's not bad if you start with this. You don't start with this. You do your work with your W1s and your W2s. You get this piece right here. You get these pieces. You then take those pieces, once you get them to their nice form because they're dividing by the Wronskian, you then integrate them in order to get your u1 and your u2, and then your particular solution is just u1 times y1 plus u2 times y2, and that's it. It seems like a lot of work, but it's not. This is actually really fast, so let me clear this and let's do one more example. I know this is a long video, but oh well. I know y'all want to see at least one more example, so here we go. Let me clear this. Okay, so for this last example problem, let's say that we have y double prime plus y equals cosine squared x. Okay, so let's just recap our y sub p we said is equal to u1 y1 plus u2 y2, and we also have that u1 prime is equal to negative, what is it? Is this one y2? I think it's y2. y2 times f of x over the Wronskian, and u2 prime is equal to y1 times f of x over the Wronskian. Okay, so these are the takeaways from all the work that we did right here. So we'll box those in. Alrighty. Okay, so, and you can see why this would be a difficult one to guess for because we have cosine squared x, so it's going to be a little bit strange. First off, let's take care of this. So we've got y double prime plus y, which is going to be our auxiliary is m squared plus 1 equals 0. Well, that means that m is equal to plus or minus root negative 1 or plus or minus 1i. Okay, so that's going to be my beta, and the alpha is going to be 0 because there's nothing that's in front of the plus or minus. Alrighty, so there should be a minus underneath there. Alrighty, so that means that my y sub c is equal to c1 times cosine x, because it's a 1 in front of that x, plus c2 sine x, right? Alrighty, which means that my y1 is cosine x, and my y2 is sine x. Okay, I'm going to need that for this. So here we go. First things first, let's do the Wronskian now that we have our y1 and y2. So the Wronskian is going to equal, well, we've got cosine and sine, so cosine x, sine x, and then the derivative of cosine x is negative sine x, and then cosine x. And so the Wronskian, which I don't need all this, do I? Is going to be cosine squared x plus sine squared x. Well, we know what that is, right? That is 1. So the Wronskian is 1, which is going to make us, we won't have to divide by anything. Well, we're dividing by 1, but it's not going to change what's up top. So now we have u1 prime is equal to negative y2. So negative sine x times f of x, which is cosine squared x. Okay? u2 prime is going to just, and that would be over w, which we know is 1, so I don't have to do that. So u2 prime is just going to be y1, which is cosine x, times f of x, which is cosine squared x. Okay? So now I can do u1, so u1 is equal to the integral of negative sine x times cosine squared x dx. And let's see, I can take the negative on the outside, so I don't have to worry about that. And I can do this one with u substitution, right? So if I make my u equal to cosine x, that means my du is going to equal negative sine x. Oh, not negative. Yeah, the derivative of that. Yeah, that is negative dx. Okay. So, well, I didn't have to take that out at all, did I? It was already already built in. Oh well, that's that seems kind of odd that it worked out so nicely. On my paper, I forgot a negative sign, but I don't think that's going to affect things too much. I might have a sign wrong. Let me make sure that I did that right. So it's negative y2, so negative sine x times cosine. Yeah, that's right. I'm not going to take that negative out. I'm going to leave it in because I need it for my du. So let me put that back in there. You saw nothing. So I've got this expression right here, which becomes u1 is equal to the integral of u squared du, which is going to be u cubed over 3 plus c, but we don't need to do the plus c for this. So this is going to equal, our u is, what's our u? We set our u up right here, cosine. So this is 1/3 cosine cubed x. Alrighty? So that's our u1. Now our u2 over here, we've got u2 is going to be the integral of cosine cubed x dx. Well, that was cosine cubed x. Well, we're going to break off a cosine. This is one of the techniques that you learned in Cal 2. We're going to break it off as a cosine x times cosine squared x dx. And then we're going to do a trig substitution for this cosine squared x and wind up with u sub 2 is equal to the integral of cosine x times 1 minus sine squared x dx. And then we're going to wind up with the integral of cosine x dx minus the integral of cosine x sine squared x dx. And so for this case, I'm going to make my u is equal to sine x, which means that my du is equal to cosine x. So this is again going to wind up being the integral of, let me actually bring it over here, the integral of cosine x dx minus the integral of u squared du, which is going to wind up, the integral of cosine x is sine x, and this is going to be 1/3 u cubed, which is going, oh, that's a minus sign. Don't worry, you don't want to mess that up. Minus sign. So 1/3 sine cubed x. Alrighty, so that's my u2. Now, up top right here, I know that my y sub p is equal to, well, we've got u1 times y1. What is u1? Well, u1 is this thing right here. So it's going to be 1/3 cosine cubed x times y1, which is cosine x. And then I'm going to have plus u2, which is down here. So sine x minus 1/3 sine cubed x times y2, which is sine x. Alrighty, so my y sub p is going to equal 1/3 cosine to the 4th x plus sine x minus 1/3 sine to the 4th x. And you can see right there why we didn't want to take a guess with that and use the undetermined coefficients method. This variation of parameters is way, way, way better. And then if I really wanted to, I could do my y is equal to c1 cosine x plus c2 sine x plus this, plus 1/3 cosine to the 4th x, try not to run beyond the bottom, plus sine x minus 1/3 sine to the 4th x. And this is our final solution right here. I'm not going to even attempt to box that in because I'll mess it up. But there you have it. That's how variation of parameters works. And you have, I'm not going to give you any homework. You already have the take home, so you can now use this method to solve one of the problems on the exam. So just focus on that. All right, hope you enjoyed it. You have a wonderful day, and I will see you later. Take care. Bye-bye.